I have a model that detects a rare disease with 99% accuracy. That sounds excellent. Here is the model. Return false. That's it. It says nobody is ill, ever. And because the disease affects one person in 100, it is correct 99 times out of 100. 99% accuracy, 0% usefulness. Accuracy, on its own, is close to a meaningless number, and today we're going to fix that. Today, why classification needs probabilities rather than verdicts, the sigmoid function and what it's actually doing, what log odds means, and why the model works in that space, and calibration, which is the property that decides whether your model's 70% means anything at all. Start with why we can't just use linear regression from last episode. Suppose we code yes as 1 and no as 0 and fit a line. Two things break immediately. The line goes above 1 and below 0, so you get predictions like 140% probability, which is meaningless. And the line is unbounded, so a single extreme x value drags the whole fit. We need something that can only ever output between 0 and 1. That's the sigmoid. It takes any number at all, from minus infinity to plus infinity, and squashes it into the range 0 to 1. Large positive input, output near 1. Large negative, near 0. Go in exactly 1/2 out. And critically, it's smooth everywhere, so we can still differentiate it, which is what lets us fit it the same way we fit anything else. The sigmoid is one line. 1 divided by 1 plus e to the minus z. That's the whole function. And logistic regression is just a linear model whose output gets passed through it. You compute slope times x plus intercept exactly as before, and then you squash. All the machinery from last episode still applies, it just gets a final step. Now, the part worth understanding properly, because it explains the whole design. What the linear part actually predicts is not the probability, it's the log odds. Odds are probability divided by 1 minus probability. So a 50% chance is odds of 1, and a 90% chance is odds of 9. Take the log of that, and you get a quantity that runs from minus infinity to plus infinity, which is exactly the range a linear model can produce. The sigmoid is simply that transformation run backwards, which gives coefficients a genuinely clean interpretation. In linear regression, a coefficient of 2 means y goes up by 2. Here, a coefficient of 0.7 means the log odds go up by 0.7 per unit of x, and e to the 0.7 is about 2, so the odds double. That's why you'll see people exponentiate coefficients and talk about odds ratios. They're converting from the space the model works into the space humans think in. Here's the shape. Flat near 0 on the left, a steep transition through the middle, flat near 1 on the right. Notice the model is most uncertain exactly where it's steepest and most confident at the extremes. And notice something practical. Where the curve is flat, large changes in x barely move the probability. So precision in your inputs matters far less out there than it does in the middle. Now, the property that actually matters, and it's the one almost nobody checks. Calibration. Take every case where your model said 70%. Of those, roughly 70% should actually be yes. If they are, the model is calibrated and its numbers are trustworthy quantities. If your 70% cases only come true half the time, your model is overconfident, and any decision you make using those numbers inherits the error. So, checking calibration takes about 5 lines. Bin your predictions 0 to 10%, 10 to 20, and so on. For each bin, compute the actual fraction that turned out yes. Plot predicted against actual. A perfectly calibrated model sits on the diagonal. Below the diagonal means overconfident, which is by far the more common direction. And it's exactly what happens when you optimize for accuracy instead of probability quality. The honest caveat, and it follows straight from episode 3. On imbalanced data, Accuracy is actively misleading, as our return false model demonstrated. Use precision and recall, or the area under the ROC curve, and please look at the confusion matrix rather than a single number. And be aware that heavy resampling to balance your classes will improve your accuracy and destroy your calibration, because you've changed the base rate the model learned. One sentence. A classifier's job isn't to be right, it's to be honestly uncertain, and calibration is how you check. Next episode, something that feels unrelated and isn't. Why the queue at the supermarket is always longer than it should be, and why a system running at 90% capacity is in far more trouble than one at 80.